first day of vacation in Yellowstone National Park.
Yellowstone National Park after an explosion that happened last month. Now Yellowstone is calling on citizen scientists to help them understand what exactly happened.
Yellowstone, a name that conjures up images of bubbling hot springs, emerald green pools, and vast wilderness stretching as far as the eye can see. For decades, it's been the ultimate symbol of untamed beauty in America's West.
Basin in Yellowstone National Park after a powerful steam explosion rocked the popular site,
drawing millions of visitors every year. Beneath its serene surface, however, lurks a far more powerful force, a restless, ancient supervolcano whose eruptions shape the continent itself. While its steaming geysers and mud pots are iconic, scientists have always wondered just how much of Yellowstone's power lies hidden, untapped, and unknown beneath our feet.
Terrifying moments caught on camera in Yellowstone National Park as a hot pool explodes, sending boiling water and debris high into the air.
Recently, a remarkable breakthrough has changed the way we look at the world beneath Yellowstone. Researchers, equipped with the most advanced 3D imaging technology yet, have managed to peel back the layers of Yellowstone's crust like never before. Their latest findings, published in a groundbreaking scientific announcement, have astonished the geological community. What they found was not merely new magma pockets or simple faults, but a sprawling, highly complex system of vents, fissures, and molten rock chambers, interconnected in ways never previously mapped. Even seasoned volcanologists found themselves revising their prior assumptions about Yellowstone's subterranean plumbing. So what does this mean for Yellowstone, for science, and for everyone living in the shadow of this colossal caldera? What new chapters of planetary history are being written right now, under the cover of forests and geysers? Could this be the start of a deeper understanding of how the world's most famous supervolcano works and evolves? Get ready, for in this episode, we delve deep into the stunning scientific revelations shaking the very foundations of what we know about Yellowstone. From the secrets of the vent network and its staggering complexity, to the mysteries of ancient eruptions and the implications this new detail brings, you're about to experience Yellowstone's underworld as never before. Is the world's most famous supervolcano revealing new chapters right beneath our feet? The revelation, Unmasking Yellowstone's hidden anatomy. What truly astonished researchers was not just the presence of magma beneath Yellowstone, but how it moved. Thanks to advances in machine learning and supercomputing, the seismic data were rendered into high-resolution visualizations that allowed scientists to track the pathways of subsurface fluids and molten rock in near real time. These visualizations revealed oscillating pressure zones, deep-flowing magma pulses, and branching steam channels that pulsed like arteries within a living body. Yellowstone, they realized, wasn't just a volcano. It was a vast, breathing organism. One of the most unexpected findings was the discovery of multiple stacked magma bodies. Previously, scientists believed there was a singular main chamber, but the tomography indicated at least two significant reservoirs. One shallow, mostly solidified zone, about 5 to 15 kilometers beneath the surface, and a deeper, more active molten region lying 20 to 45 kilometers below. These are not isolated compartments. They are connected by rising columns of partially molten rock, forming a tiered magmatic structure akin to a two-story engine room beneath the park. Adding to the intrigue was the identification of a massive hydrothermal sponge layer. This porous zone, saturated with superheated water and volatile gases, acts as both a pressure buffer and a potential explosion trigger. Under certain conditions, trapped steam and gas could cause sudden overpressurization, leading to phreatic explosions, violent steam-driven blasts that require no fresh magma to be deadly. The 3D model showed that these spongy layers are more widespread than anticipated and lie much closer to frequently visited areas than previously assumed. Furthermore, geochemical analysis of vent emissions, hydrogen sulfide, carbon dioxide, helium isotopes confirmed that new gases were reaching the surface, suggesting changes in how heat and materials migrate through the crust. Some researchers speculate that tectonic shifts or regional stress patterns may be subtly rearranging how magma and gas flow through the system, possibly reactivating old faults or vents that had long gone quiet. These findings, though not a sign of imminent eruption, are reshaping how scientists monitor Yellowstone. The U.S. Geological Survey, USGS, has begun expanding its sensor arrays, increasing GPS and seismic monitoring, and even incorporating AI-driven anomaly detection systems. The goal: to capture subtle signals before they amplify into serious geological events. This isn't just about Yellowstone anymore. It's a template for understanding other supervolcanoes. What lies beneath the park is no longer a mystery. It's a message written in magma, waiting to be read. A labyrinth of heat tracing Yellowstone's underworld. Among the most striking revelations from the new modeling efforts is the realization that Yellowstone's interior behaves not like a single volcano, but more like a complex volcanic province, a distributed system where multiple subsurface nodes interact, transfer energy, and influence one another in real time. These nodes, consisting of magma pockets, gas-rich cavities, and hydrothermal reservoirs, form a dynamic interplay that changes seasonally and even daily, depending on external influences such as snowmelt, rainfall, and tectonic strain. Researchers discovered that in some areas, fractures acted as one-way valves, allowing gases to rise without necessarily permitting magma to follow. This has profound implications. It suggests that not all gas emissions are immediate precursors to magma movement, but may instead reflect deep depressurization events or shifts in internal plumbing. In essence, Yellowstone's underworld is not only complex, but also highly adaptive, rerouting pressure and material flow, depending on stress conditions and rock permeability. In one newly identified zone beneath the western caldera rim, seismic sensors recorded a consistent swarm of microquakes over a 2-month period. These weren't classic tectonic tremors, but low-frequency events, often associated with fluid movement and deep pressurization. Temperature modeling for this area suggested a steady increase in subsurface heat, possibly due to magma slowly intruding into a previously cooler section of the crust. Though not alarming in isolation, these signals prompt increased scrutiny and reinforce the importance of detailed spatial analysis in hazard forecasting. The implications extend to surface hydrothermal systems as well. The branching nature of the subsurface conduits explains why geysers that are physically distant from one another, sometimes kilometers apart, can erupt in synchronized fashion or affect each other's timing. For instance, shifts in pressure in a lateral feeder system might cause one geyser to quiet while triggering another to activate, much like valves along a shared pressure pipeline. This phenomenon has puzzled scientists for years, but now appears grounded in the physical connectivity of Yellowstone's deeper structures. Moreover, the new data illuminate why some areas of the park, such as Norris Geyser Basin, are unusually volatile. Beneath these zones, tangled webs of fractures act like funnels for both heat and volatile gases, creating pressure traps that can discharge explosively when thresholds are crossed. These insights are already feeding into updated risk maps and are guiding new placements for monitoring stations, ensuring that Yellowstone's shifting heartbeat remains under constant watch. Echoes of the ancient past, Yellowstone's volcanic legacy. What makes Yellowstone particularly daunting and unique is the sheer scale and diversity of its eruptive history. The 3 super eruptions, spaced hundreds of thousands of years apart, are the dramatic punctuation marks in a far longer narrative of volcanic evolution. But in between those massive blasts, the volcano remained active, silently shifting, intruding magma, venting gas, and reshaping the landscape through more subtle geological processes. These quiet periods, geologists now understand, are anything but inactive. Recent research suggests that the smaller lava flows, like those of the Pitchstone Plateau and the Central Plateau, were not mere afterthoughts to the super eruptions, but essential steps in the long-term stabilization of the magma system. Each of these eruptions helped relieve pressure, redistribute heat, and change the geometry of the underground reservoir. By modeling how these smaller events played out, scientists are now better able to trace the long-term cycles of pressurization and decompression that define Yellowstone's behavior. The geological record, now mapped with far greater precision thanks to LiDAR and satellite analysis, also points to a pattern: periods of relative quiet, often lasting tens of thousands of years, followed by phases of increased hydrothermal explosivity or new vent formation. These patterns are deeply tied to the buildup and release of gases in Yellowstone's hydrothermal sponge, a zone of porous rock that becomes pressurized as volatiles rise from the underlying magma. When that pressure surpasses the strength of the overlying crust, explosions can occur, even in the absence of lava. By examining the stratigraphic layers of ancient ash beds, tephra deposits, and hydrothermal ejecta, geologists have correlated these surface records with newly imaged vent systems below. For example, certain explosive events align directly above the intersections of multiple underground conduits, suggesting that these fracture clusters act as geological release valves during high-pressure episodes. These intersections may also be the weak points most likely to reactivate in the future. Even the massive caldera itself tells a story of collapse and renewal. Each time the magma chamber emptied during a super eruption, the overlying crust caved in, forming a new depression. But over time, magma intruded again from below, causing the surface to rise, only to collapse again in the next great event. It's a breathing cycle spanning millennia, and Yellowstone's surface is still moving subtly today, rising and falling by centimeters each year. This breathing earth, this slow inhale and exhale of molten power, is the legacy of a restless system, shaped by forces that began long before humans walked the continent, and which will continue long after we are gone. Signs from the depths, decoding, seismic, and thermal clues. To appreciate the subtlety of Yellowstone's behavior, it helps to understand just how sensitive and sophisticated its monitoring system has become. The Yellowstone Volcano Observatory, YVO, a collaborative effort between the U.S. Geological Survey, the University of Utah, and the National Park Service, has created one of the densest and most advanced volcano monitoring networks in the world. With more than 60 seismic stations, continuous GPS sensors, thermal infrared satellite overflights, and high-frequency gas monitors, the system serves as a digital stethoscope for the park's deep, dynamic engine. A key revelation of recent years is the behavior of seismic swarms. These events often consist of dozens to hundreds of micro-earthquakes over several hours or days. While individual quakes rarely exceed magnitude 3, their grouping and migration patterns are significant. Some swarm appear to track rising steam fronts or pressurized fluids pushing through brittle rock, like tiny pressure relays sounding off in sequence. Others suggest shear movement along old faults reactivated by thermal expansion or magmatic adjustments at depth. Mapping these patterns in 4D across space and time helps volcanologists visualize underground pressure paths that would otherwise remain invisible. Thermal data adds yet another layer of complexity. By integrating infrared imaging from satellites with ground-based temperature loggers, scientists have observed localized heat surges in unexpected regions. Some of these silent hotspots don't show traditional hydrothermal activity at the surface, yet radiate significantly more energy than their surroundings. These may be areas where magma has intruded closer to the surface, or where old vent networks are being reactivated by upward heat migration. In either case, these anomalies are logged, modeled, and tracked continuously for change. Chemical monitoring of gases and hydrothermal fluids reveals Yellowstone's volatile chemistry in flux. Spikes in carbon dioxide and sulfur dioxide, shifts in helium isotope ratios, or changes in dissolved chloride concentrations in springs are all carefully cataloged. These changes can suggest new pathways for gas escape or shifts in subsurface magma degassing behavior. For example, an increase in 3 He to 4 He ratios often indicates a more primordial magmatic gas source rising from deep within the mantle, an early clue that something below is stirring. The integration of all these clues, seismic, thermal, geodetic, and chemical, gives scientists a fuller, more nuanced view of the system. It doesn't predict eruption timelines, but it gives early warnings. And in a place as dynamic and unpredictable as Yellowstone, such foresight is the best defense against surprise. Surveillance at the surface, geysers, lakes, and shifting ground. Yellowstone's surface tells a story every bit as dynamic as the subsurface magma system. Geysers and hot springs may appear timeless to tourists, but to scientists, they're dynamic instruments, fluid pressure gauges that respond instantly to shifts below. Changes in eruption intervals, water chemistry, or even the direction a geyser sprays can serve as early indicators of deeper changes in the hydrothermal network. One of the most compelling recent examples is Steamboat Geyser, the tallest active geyser on Earth. After lying mostly dormant for decades, it suddenly reawakened in 2018, entering a period of frequent eruptions that puzzled researchers. Why the change? Subsequent analysis revealed subtle thermal and hydrologic changes in the surrounding area. Some scientists believe that increased underground heat flow or a shift in vent alignment allowed superheated water to reach the surface more easily. Steamboat became a live case study in how volatile and unpredictable these systems are. Similarly, in the Norris Geyser Basin, entire zones have come alive with new features. In one instance, a dormant spring began bubbling vigorously, creating a new thermal feature that forced the temporary closure of nearby boardwalks. These surface transformations, while often small in scale, have outsized implications. They suggest that underlying steam pathways or heat channels are adjusting, even without seismic triggers. Yellowstone Lake, vast and tranquil on the surface, conceals a geologically active floor. Using sonar mapping and remotely operated underwater vehicles, scientists have discovered numerous vent fields, some spewing warm water, others releasing gas bubbles laced with CO2 and hydrogen sulfide. These sublacustrine hydrothermal systems mirror those found in deep ocean ridges, providing critical analogs for both volcanic behavior and even the search for life in extraterrestrial oceans like those on Europa or Enceladus. More urgently, they're monitored as potential sites for hydrothermal explosions, a rare but devastating phenomenon where water superheats underground and erupts violently when the pressure cap fails. In tandem with hydrothermal changes, ground deformation continues to reshape the park's landscape, sometimes gradually, sometimes abruptly. GPS and INSAR satellite measurements show slow uplift or subsidence in certain areas, including the floor of Yellowstone Lake itself. These changes often correspond to shifts in magma pressure, the draining or refilling of underground reservoirs, or localized crustal adjustments. Collectively, these surface clues reinforce one essential truth: Yellowstone is not a sleeping giant. It's wide awake, breathing, boiling, and reshaping itself beneath the feet of every visitor who walks its fragile crust. Warning or wake-up call, implications for the future. Though Yellowstone's new 3D vent model does not point to an impending eruption, it undeniably sharpens the tools of anticipation. For the first time, scientists can see not just where heat and pressure are building, but how and where they might be redistributed across a complex, evolving volcanic system. This improves not only long-term hazard forecasting, but also real-time risk assessment for events like phreatic, steam-driven explosions and regional ground deformation. Small, hydrothermal explosions, while far less dramatic than a super eruption, still pose serious risks, particularly in heavily visited areas like Norris Geyser Basin or Upper Geyser Basin. With this refined model, geologists can now identify vent intersections, pressure bottlenecks, and fault-aligned thermal zones with far greater precision. This allows land managers and emergency planners to make more informed decisions about trail closure, infrastructure placement, and emergency response protocol. At a broader level, the model contributes to a paradigm shift in how supervolcanoes are monitored and understood. Rather than treating systems like Yellowstone as static time bombs on a countdown, scientists now approach them as dynamic systems, constantly adjusting, releasing pressure, and evolving over time. This reframing moves public discourse away from sensationalism and towards sustained, science-driven stewardship. Environmental scientists are also drawing on the findings to explore downstream impacts. The alteration of vent flows, water temperatures, and gas emissions could change microbial ecosystems that thrive in geothermal habitats, many of which are biologically unique and remain poorly understood. Aquatic ecosystems fed by geyser runoff may also experience changes in pH, salinity, or dissolved gas content, with cascading effects on fish, algae, and surrounding vegetation. Living with a restless giant. Yellowstone, with all its splendor and restless energy, remains a living reminder of the planet's dynamic forces and of our place within them. The vent network, now mapped in more detail than ever before, is a testament to how much we still have to learn from nature's hidden depths. Today, the supervolcano sleeps, the landscapes above continue their cycles, and life, both human and wild, flourishes atop ancient fire. Every micro-earthquake, every burst of heat, every branching vent discovered beneath the forests and lakes adds a line to Yellowstone's ongoing story, one written in fire, stone, and patient discovery. In labs, research stations, and meeting rooms, geologists, physicists, and park rangers parse the latest data, learning more with every passing season. What do you think? Is Yellowstone simply cycling through another page in its deep, ancient story? Or do newly mapped details reveal mysteries science has yet to fully unravel? Join the conversation below. What did you find most astonishing about Yellowstone's secret underworld? What questions do you hope the next wave of research will answer? If you enjoyed this exploration into Yellowstone's hidden power, remember to like and subscribe for more episodes uncovering our planet's incredible natural wonders, and keep your curiosity alive. On this wild and unpredictable Earth, the next great discovery may already be rumbling beneath our feet. Stay curious and keep exploring.